And we don't care about statistical proofs. We just want to know that this is one possible solution, which is by far the most widely used, but there are other ones. So let's have a look at this slide. And before looking at this slide, let me see if I have another one. Yes, this is another one which is extremely important because it's non-quadratic. Another way of getting rid of the sign is by taking the absolute value. So another possible solution is to compute the sum of the absolute value of the errors. In this case, it is divided by, at each time step, it's divided by the observation. And this is called mean relative error. Sometimes it could be tricky, the subjective function, if you have observation tending to 0 or taking a value of 0, then it's not defined. And also if the observation tends to 0, it may give weird behaviors. So basically one should use particular care to make sure that x is never close to 0 when the subjective function is used. But this is indeed an attractive option. Or another attractive option, which is not listed here, is just the sum of the absolute value of the epsilon. And a different objective function lead to different model performances. If you square the error, usually you get better results in the reproduction of the peak flows. If you don't square the error, if you take the absolute value, you get better results in the reproduction of the low flows. And you may wonder why. It's quite simple to understand why. If you think to a river discharge of close to 0, what is the maximum mistake that you can make? If the river discharge is 0.5, the maximum mistake that you can make, is there is not a maximum, but you are around this order of magnitude. So if you make an error of 100%, it's a mistake of 0.5. So basically, in the reproduction of the low flows, usually you have very small errors. In the reproduction of the peak flows, if you have a peak flow of 1,000, you may easily make a mistake of 200, and still it's a good result. So basically, what happens when you square these errors? The errors close to 0 becomes even smaller. The errors that are instead large, they become much larger. So basically, you put more weight on the large errors and less weight on the small errors. This is why, with the least squares, you focus on floods. With the absolute values, you focus on droughts. I hope it's clear. And you may also try. You will try. So basically, this is another interesting option, because as water resources managers, we often use the sum of the absolute errors instead of the squared errors. Now let me go back to the previous slides. These are all quadratic measures, and I'm not interested in this one. I think it is, also here there is a problem with the font. And this, I think, this is the hat, which is displayed as an F. I think it's a problem of my PC. Probably if you visualize it on your PC, you don't get this problem. But in any case, this is the up. But as I said, I'm not interested much in this correlation coefficient. I would never ask him ask it at the exam. The Nash efficiency, instead, it's an interesting objective function, and please learn it, because it is extremely important, and I may ask it at the exam. And basically, it's quadratic. And let me just explain how it works. At the numerator of this fraction, you have the sum of squares. So you have this relationship that you can see on the blackboard. So here you have the sum of squares. So you understand that it's quadratic. And this is varying depending on the parameter vector theta, because it's at x that is varying depending on parameter vector theta. So basically this quantity here in the numerator, which is the sum of squares, of course depends on the parameter vector, but it's the only one here. The rest is fixed, because one is fixed, and the denominator is just, look at here, this is the average of the x. So you subtract from each observation the overall mean value, and you square it. This is fixed. I mean, once that you have the data, it's fixed. So basically, what is the meaning of this fraction? Look, it's a comparison. At the numerator, we have the least squares. We have the squares, the sum of squares at the numerator. At the denominator, we have the sum of squares given by a hypothetical model which simulates the variable by taking the mean value. So let's assume that our model gives the simulation by taking the mean value of the data. This is a very trivial model, very trivial one, because if you have to make a prediction and you don't know anything, you just have a sequence of data, what would be your guess for the next value? If you don't have any other information, you would, by intuition, compute the average. Of course. And this is a very trivial model for making a prediction of river flows. If you have a series of data, you don't have time to gain any other information, and somebody asks you, what is the river flow for tomorrow? You compute the average. This is a trivial model. And therefore, at the denominator, you see the sum of squares that you would obtain with this trivial model. You have a question? Sorry.
Yes.
Yeah, please.
How practical is the trivial found answer to the river flow? Like you said, by intuition, someone could
By intuition, I mean, if you have to give a guess, and you have a series of data, and you don't have any time to develop any model or any means, wouldn't you compute the average to deliver a prediction? And this is reasonable. I mean, if you don't have any, and then if you have time, you may look at the season, and you may take the seasonal average. Like I am in August, I have to predict the river flow for tomorrow. I may say, okay, let me look at the past Augusts and compute the average only of them. But the intuition is that the average is a very trivial model. Or if you had to guess, for instance, you toss a coin and you have to guess the next result, you would say 50% head, 50% cross. And sorry, head or cross? Yeah, head or cross, I think. Tails, yeah. You would say this because it's a computation of the average. The average result is in between, so 0.5, 0.5 of probability. So basically, this is a trivial model, and basically what you do here is comparing the error that you get from your Reinforth model with the error that you would get from the trivial model. Now, let's see, what is the upper value of this Nash-Sutcliffe efficiency? So let's suppose that the model is perfect. If the model is perfect, sorry, if the model is perfect, you would get a 0 at the numerator because you don't the difference between observed and simulated is identically 0. So if the model is perfect, you would get a Nash efficiency of 1. Now, let's suppose that your model performs as the trivial model, which means that basically you would get a comparable sum of squares, and then you would get 1 from the fraction. 1 minus 1 is 0. So basically you get an efficiency of 0 when your model performs more or less as the trivial model. From 0 and 1, you have a situation in which the model performs better than the trivial model with increasing performances. And if you get a negative efficiency, which could be, it means that your model performs worse than the trivial model, so it's really bad. So basically the efficiencies varies from minus infinity to 1. And usually in hydrology we say that the least that we want is 0.5. Less than 0.5 is really a bad model. And we say that a model is acceptable when it's higher than 0.7, and it's good when it's higher than 0.8, is very good when it's higher than 0.9. Typical efficiency depends on the model complexity, on the catchment, but it's difficult in hydrology to go over 0.7, usually. unfortunately, you get efficiency between 0.5 and 0.6, which is not really good. Please.
I didn't understand these last things. You said that if the model is perfect, we have 0 at the numerator.
Yeah.
Right? So below,
the result is 0.
the result is 0 then.
And your efficiency is 1.
Because below I don't get 0.
No, below is unchanged.
Okay.
It doesn't depend on the parameters. It's a fixed quantity. You have the data, you compute the average, and then that's it.
I have a doubt. Let's assume that our function, I mean the data of our function, is very wide, has very many different values. So our denominator is a big number. So this allows us to have big errors.
Yes, but you know, basically the denominator is a big number because you have a variability of the series. So basically the denominator is an indicator of variability of the series. And so if your series is highly variable, you expect that the model simulation is highly variable as well. But on the other hand, if you get a variability of the error that is comparable to the variability of the series, it means that the model is really not useful. Because what is the purpose of your model? You have a series that is variable. The model should explain the variability. And if it is able to explain the variability, the error is close to 0. And then here you have a huge number. Here you have a number that is close to 0. You get close to 0 independently of the variability of the series. And then your model could be not perfect and the error increases. Of course, you can tolerate an higher error when the series is highly variable, because it's by understanding. You understand that by intuition that if you have a huge variability, it's much more difficult for the model to reproduce it. And therefore, you can tolerate an higher error. I agree with you. What you said is fine. But let's suppose that you have, let me make a graph, a picture. Let's suppose that you have a series with two hydrographs, I mean two axes. And the first one is basically slowly varying. Okay, and the second one is much more varying. So, in this case, basically, let's drive a completely wrong simulation by chance. You see that the error is still very reduced because there is not much variability. But the problem is that it's completely wrong. Why? Because the variability of the error is comparable to the variability of the series. In this case, let's suppose that you have a good simulation, but still, simulation is quite good, but still, you see that the error is much more variable with respect to the previous case. But given that the variability of the original series is higher, you are happy as well. You are anyway happy because, not as well, you are much more happy here than here, even if the error here is smaller. It's like if you look at drought and peak flows. With peak flows, you can tolerate an error of 200 cubic meters per second over 1,000 because it's 20%. In this case, if you have droughts, I mean, the error is much lower, but in relative terms, it may be 200%. So what's important is the relative error. And the relative error, in order to obtain a measure of the relative error, you have to divide times the variability. If you have a higher variability, it means that you can tolerate a higher error. It's clear. It's not easy to explain, but it would be better to make an example. And maybe that when we develop the exercise, we can make it. Any other question? Okay, and let me just say a couple of things. Let me see if I have the network. Just 1 second. No, I don't have it. But I just wanted to say one thing, and between the lecture that I used for rainfall runoff modeling and the lecture that I used for calibration, there is one other document that gives to you some more details on the Reynolds transport theorem. And these details, I'm not focusing on them because I don't think they are important, but this document proves how you can get from the Reynolds transport theorem the continuity equation and the energy balance equation and the momentum balance equation. And so I think it is a useful reading, and it should be also clear. There is one other thing that I wanted to tell you before we leave. I think I already said this, but I wanted to make it more clearer, let me say. And when I introduced the Reynolds transport theorem, I spoke about extensive property and intensive properties. I want to stress that intensive means property per unit mass of fluid, because I am not sure, I should check the video, I may have said for unit volume, which wouldn't be correct. So when you have a property which refers, a bulk property or bulk, I don't know how to pronounce in English, which refers to a volume of fluid, you may consider the extensive property, which is the total of this property for the volume, like the mass. The intensive property is the total divided by the mass of fluid, like mass density. Okay? This is important to keep into account. I'm not sure if I said that per unit mass or unit volume. I had this doubt, maybe I was wrong, so I wanted to make it clear. And because the Reynolds transport theorem, I may ask it at the exam, as I said, and it's important that you state what the symbols are clearly. And the other document which I just shown to you, this is not as important. It's important if you are interested in knowing more, but I'm not asking how you can get the continuity equation from the Reynolds transport theorem. It just suffices for me that you know how to write it down and the meaning of the symbols. That's it. And next time we move forward with validation and then again rainfall runoff modeling. Ma invece l'intensive
siamo sempre nella
on Thursday the room is 4.1, okay, 4.1 the room, and keep some plugs and how to say long wires, prolunghe we say in Italian because it may be difficult to connect the PC at the network, power network. Really in 4.1, are you sure? Ah, okay, that's fine. Okay, they say that there are plugs there, so no problem. See. Ci sono anche delle comunicazioni delle formule complicate, di dare anche un peso diverso alle ore, a seconda che sia positivo, però al di là della quale non ci sono delle altre cose. Sì, però il problema è che praticamente su questo vettore bisogna sempre trovare una misura di somiglianza del vettore con l'obiettivo e deve essere un valore.
Deve essere tendente a zero,
No, sì, certo, tendente a zero, però voglio dire, lei ha un vettore, no? Allora come misura la distanza tra due vettori? Perché
ma non lo devo fare in questo modo, lo capisco il conto.
cioè, non ho capito, allora lei ha un vettore di errori, poi
Esatto, e ogni costante il valore deve essere zero, quindi non devo, cioè devo cambiare finché non diventa zero.
sì, però di fatto non diventa mai zero, quindi
Sotto una certa soglia. Quindi.
sì, però il problema è Enrico.
Ciao,
No,
ho mandato
perfetto.
messaggi,
Sì,
mail.
sì, no, aspetta un secondo, allora che mi fermate, senti, lo vediamo giovedì, venerdì, d'accordo. Aspetta un secondo che hai mandato, perché adesso ho spento il telefono.
No, ma io se ripego 5 minuti
Allora,
adesso.
perché mi ha telefonato Alessandro Villa, però io devo scappare, ci sentiamo domattina.
Adesso volevo anche... Sì, un attimo da te, fai 10 minuti per noi.
Io ce li ho 10 minuti, mi devi solo far tirare su tutto. Ciao.
But thank you, please.